In recent years, the combination of drones and advanced mathematical models has transformed environmental monitoring. One of the most powerful and intriguing developments is the application of fractal algorithms in analyzing terrain and vegetation, particularly trees. Fractals, mathematical sets that exhibit self-similar patterns at varying scales, have long been used to describe complex natural phenomena. When applied in conjunction with drone technology, they can provide deep insights into ecological systems, particularly for mapping and counting trees in large areas. This article explores the intersection of fractal mathematics and drone-based environmental analysis, with a focus on how fractal algorithms can be used to monitor trees and terrain. We'll discuss the role of drones in collecting environmental data, delve into the fundamentals of fractals, and examine how fractal dimensions can help estimate tree numbers and patterns. We will also review current tools and software capable of implementing these algorithms, the challenges involved, and the potential for future development in the field. Drones have become a vital tool in the fields of environmental science, conservation, and land management. Their ability to capture high-resolution imagery and sensor data from previously inaccessible or difficult-to-reach locations has revolutionized ecological monitoring. A typical drone equipped for environmental analysis might include multispectral cameras, LiDAR systems, and infrared sensors. These tools allow the drone to collect data on various aspects of the environment, including vegetation health, soil moisture levels, and even animal populations. One of the most significant applications of drones is in forestry, where they are used for tasks such as tree inventory, canopy monitoring, and forest health assessment. Traditionally, these tasks required labor-intensive, time-consuming surveys conducted on foot. Drones enable researchers to cover vast areas quickly, providing real-time data that can be analyzed with far greater accuracy and efficiency. However, despite the numerous advantages drones offer, the data they collect is often highly complex and difficult to interpret without the aid of advanced algorithms. This is where fractal mathematics enters the picture. Fractals are mathematical structures that repeat themselves on different scales, creating intricate patterns that remain consistent regardless of the level of magnification. This property, known as self-similarity, makes fractals ideal for describing the complexities of natural systems. Examples of fractals in nature include the branching patterns of trees, the veins in leaves, and the structure of river networks. Fractal geometry has been instrumental in the study of natural phenomena because it can describe irregular shapes and complex patterns that traditional Euclidean geometry cannot. A key concept in fractal geometry is the fractal dimension, a measure of how completely a fractal fills space as you zoom in on it. This concept can be applied to terrain analysis, tree distribution, and forest density. In forestry, trees and their canopies often follow fractal-like growth patterns, meaning that the distribution of trees and branches can be described using fractal dimensions. This makes fractals a powerful tool for analyzing the data collected by drones. Forests are ideal environments for the application of fractal analysis because they exhibit self-similar patterns at various scales. A single tree has a fractal-like structure, with branches that split into smaller branches and twigs, each following the same basic rule of growth. Similarly, forests themselves follow fractal patterns, with patches of trees distributed across the landscape in self-similar clusters. The fractal dimension is a numerical value that quantifies this self-similarity. For instance, if the fractal dimension of a forest is close to 2, it suggests that the trees are distributed more like a surface, whereas a fractal dimension closer to 3 suggests a more volumetric distribution. The box counting algorithm is one of the most common methods used to calculate the fractal dimension. This method involves dividing a map or image into a grid of boxes and counting how many boxes contain a part of the forest. The process is repeated at multiple scales, and the fractal dimension is determined by how the number of occupied boxes changes as the box size is reduced. In practice, this means that fractal algorithms can be used to estimate the number of trees in a given area by analyzing how tree clusters are distributed across the terrain. To apply fractal algorithms to forest data, the first step is data acquisition using drones. The drone flies over the forest, capturing high-resolution images or 3D data using tools like LiDAR, light detection and ranging. Once the data is collected, it must be processed to create a digital representation of the forest. This might involve generating a 3D model or a canopy height model, which is then analyzed using fractal algorithms. The box counting algorithm, for example, can be applied to these digital models to estimate the fractal dimension of the forest. By comparing fractal dimensions across different regions, researchers can identify patterns in tree distribution and estimate the total number of trees in a given area. Fractal algorithms also offer a unique advantage over traditional methods because they can account for the irregular, non-linear patterns that occur in nature. Forests are not perfectly uniform. They have areas of dense tree growth and areas where trees are sparse. Fractal algorithms can capture these variations more effectively than grid-based or linear methods. Let's consider a case study where drones were used to monitor a forested region in the Pacific Northwest. The goal of the study was to estimate the number of trees in a 100-acre area and assess the overall health of the forest. The drone was equipped with a high-resolution RGB camera and a LiDAR sensor, which allowed it to capture detailed images and 3D data of the forest canopy. Once the data was collected, it was processed to create a 3D model of the forest. Researchers applied the box counting algorithm to this model, calculating the fractal dimension of the tree distribution. By comparing the fractal dimension to known values from similar forests, they were able to estimate the number of trees with a high degree of accuracy. In addition to counting trees, the fractal analysis revealed areas where tree density was significantly higher or lower than expected, providing insights into the health and structure of the forest. This information was used to guide forest management efforts, including selective thinning and reforestation projects. LiDAR technology is particularly well suited to fractal analysis because it provides detailed, three-dimensional data that can be used to create highly accurate models of forested landscapes. Unlike traditional cameras, which capture only the surface of the canopy, LiDAR can penetrate the forest canopy to provide information about the height and structure of trees, even in dense forests. By combining LiDAR data with fractal algorithms, researchers can analyze the structure of a forest at multiple scales. For example, they can study the distribution of trees at the level of individual branches, the canopy as a whole, or the entire forest. This multi-scale analysis allows for a more comprehensive understanding of forest structure and health. Several software tools are available for implementing fractal analysis in forestry, many of which can be integrated with drone data. Some of the most popular tools include Pix4D, a software platform that specializes in converting aerial images into 3D models and maps. Pix4D can process data from drones and generate digital terrain models, which can then be analyzed using fractal algorithms. DroneDeploy, a cloud-based platform that provides tools for analyzing drone data in various industries, including agriculture and forestry. DroneDeploy allows users to create orthomosaic maps and 3D models, which can be used in fractal analysis. Software like ArcGIS and QGIS can process LiDAR data to create detailed 3D models of forested areas. These models can be used to calculate fractal dimensions and analyze tree distribution. For more advanced users, custom solutions can be developed using programming languages like Python. Python's libraries, such as OpenCV and NumPy, provide the tools needed to implement fractal algorithms on aerial images and 3D models. Additionally, ImageJ, a widely used image processing software, offers fractal analysis plugins that can be applied to tree counting and forest monitoring. Researchers and developers can also leverage the R programming language and its FractalDim package, which offers several methods for calculating fractal dimensions from spatial data. R's powerful statistical capabilities make it an excellent choice for analyzing large datasets collected by drones. One of the primary advantages of using fractal algorithms in tree and terrain analysis is their ability to provide precise, scalable results. Traditional methods of forest monitoring, such as ground surveys or simple image analysis, often fail to capture the complex, non-linear patterns that occur in nature. Fractal geometry, however, is specifically designed to describe these irregular patterns, making it ideal for analyzing natural systems like forests. Fractal algorithms can also be scaled to analyze forests of varying sizes. Whether the goal is to study a small grove or a vast forest, fractal dimensions can be calculated and compared across different regions, providing valuable insights into tree density and distribution. Combining drones with fractal analysis also offers significant cost savings and increases in efficiency. Drone-based surveys are far less labor-intensive than traditional ground surveys, and the data they collect can be processed quickly using fractal algorithms. This reduces the time and cost required to monitor large forested areas, making it easier for researchers and land managers to track changes in forest health over time. Despite the many benefits of fractal-based analysis, there are also challenges associated with processing the large volumes of data generated by drones. High-resolution imagery and LiDAR data can be difficult to manage, particularly when dealing with large areas. Additionally, fractal algorithms require significant computational power, which can be a barrier for researchers with limited resources. Another challenge is the inherent variability in natural systems. While fractal algorithms are excellent at describing self-similar patterns, they may struggle to account for the many factors that influence tree growth and distribution, such as soil composition, water availability, and human activity. As a result, fractal analysis is most effective when used in conjunction with other methods, such as ecological modeling or field surveys. One of the most exciting developments in the field of fractal analysis is the integration of machine learning algorithms. By training machine learning models on drone data, researchers can automate the process of identifying fractal patterns and calculating fractal dimensions. This has the potential to greatly improve the accuracy and efficiency of tree and terrain analysis. While this article has focused on the use of fractal algorithms in forestry, the same principles can be applied to a wide range of fields, including agriculture, urban planning, and disaster management. For example, fractal algorithms could be used to analyze the distribution of crops in agricultural fields or to map the spread of wildfires in real time. The integration of drone technology with fractal algorithms represents a powerful new approach to environmental analysis. By leveraging the self-similar patterns found in nature, fractal algorithms provide a precise and scalable method for counting trees and analyzing terrain. While there are challenges involved in processing drone data and accounting for natural variability, the potential benefits are significant. As technology continues to advance, the combination of drones, fractals, and machine learning is likely to play an increasingly important role in environmental monitoring and conservation efforts. With the ability to process vast amounts of data quickly and accurately, fractal-based analysis is poised to revolutionize the way we monitor and manage the natural world.